So we worked with parabolas before. We're going to look at parabolas and how they relate to conic sections. So conic sections is kind of how things are cut out of cones, and it's looking at things in a more 3D light, and so more geometrically, and trying to see how we would actually use some of these things. So we're going to look at parabolas with the idea of how they could be used, and looking at them in more of a three-dimensional way. But we want to go ahead and so we're going to look at some new things. We're going to look at focus, and we're going to look at directrix and focal diameter. And when we see, let's graph one. So if we have y equals x squared, we're going to graph that, and hopefully we know this. It's going to be at 0, 0. We'll go through 1, 1. We'll go through 2, 4, and negative 2, 4. And it should look something like this. And when we're looking at this in more of a three-dimensional light, we kind of want to know a few different things about this. So we have things called a focus, and focus is really just this idea that there's this one point that is pretty equidistant to the other points on the parabola. So basically it's the idea of where that curve is pointing toward. And so it's going to lie in your axis of symmetry. And we're going to say that it lies P away. So we're going to have, since it's on 0, we're going to have this at 0, P. The directrix is kind of saying what would the opposite of that be. So if this is my focus and that lies P away, the directrix is kind of the opposite of it. And it's a line, and it's a line that lies at negative P. And so if you think of two uses of a parabola in three-dimensional space, you could have something like a satellite. The focus would be where that is pointing toward. So it's kind of going toward this focus. Or you could have a parabola with a bridge, and the directrix would be like the bridge part. Where is the strong line coming from that parabola? Focal diameter is just saying the length, the width of the parabola, I guess. And if we have the correct focus, then this is actually 2p from the edge of the parabola, that distance. So therefore the other distance would also be 2p, so the focal diameter would be 4p. Okay, so we're using this thing p to show this distance and this distance. Both of these distances are just p. And we actually can write a parabola, and can derive it, should be in your book, but we can write a parabola with that distance and call it, and it's just going to basically be x squared equals 4py. So I can use this equation as my geometric equation of a parabola. And if I can write stuff in this geometric equation, I could find out where my focus is, where my directrix is, and where my focal diameter is. This is true with my x equals y squared. X equals y squared is the exact same parabola, but it should be sideways. And hopefully this makes sense. 0, 0. This time when y equals 1 or negative 1, then I get those points. When y equals 2 or negative 2, I get the points further up. So it's just the exact same parabola, but sideways. So with our y equals x squared, we got these. And since this was a horizontal line, I should probably write that as y equals. Our x equals y squared, it's just basically the opposite. Focus is still p, but it's going to again be where it's pointing towards. So it's going to be p comma, in this case 0. Directrix would this time be a vertical line because it'd be opposite. So directrix would just be x equals negative p. Focal diameter would be the same because it's a length. So if I wrote this in a geometric standard equation, y squared would equal 4px. So I'm going to use those two ideas to find my focus and my directrix of some parabolas, and then see if I can even write an equation of one.